This is Embedded Systems Design class, where we will discuss embedded systems and microcontrollers. Specifically, we'll focus on one of the common microcontrollers from Microchip company, which is PIC24. But today we will start with lecture 1, which is basically an introduction. So, and today we will talk about the concept of microprocessors, the microcontrollers, and then we will define embedded systems. We will see some of their applications, and we will finish this talk with restating some fundamentals. So, the engines for digital system, as you can see here, we make a simple list where we started digital system design with gates that are composed of transistor. And then we moved to ROM, or the read-only memory, with many types, like the ROM and PROM, EPROM, and EEPROM. And we also have the programmable logic array, or the PLA. We also have PAL, programmable array logic, and the CPLD, the complex programmable logic device. And all of these are old chips that are very well known since a long time ago in digital systems, since the beginning of 1950s. So we, as we said, we talked about the gates, the ROM, the PLA, the PAL, and the CPLD. Now, for the digital system, the boom started, in my opinion, with FPGA, which is the field programmable gate array, like the one you see here from Xilinx. And then, since actually the beginning of the digital system, meaning the starting with the Moore's law in 1965, the microprocessor idea became apparent in many companies, and people started using them for processing. So that's one example of the microprocessor from Intel, the Core i7. We also, we will discuss the microcontrollers. And here we have a microcontroller from Microchip. This is basically PIC18. And we also have the DSP, the digital signal processor, which is basically an analog application. So in this course, we will focus on microcontrollers, because this is what is used in all the embedded systems nowadays. And we will compare it with the microprocessor that everybody knows. So, as a computer essential, we know that the core of any computer is the central processing unit, or the CPU. That is the center of the computer, and it interchanges data from data memory, where you store variables, and the program memory, where you store your code. And you interact with the outside world with input and output devices. As you know, for example, like input, you have a keyboard, the output, you have the screen, as an example. We also have instruction sets. We have two types. We know that the instructions is the language of the computer. You give the computer instructions, and one by one, the computer or the CPU start executing them. So we have two types, the CISC and the RISC. The CISC is a complex instruction set computer. This is one example where you have a multiplication instruction, And it has two variables that you multiply together and you store the result in another variable. We all know that the multiplication is basically repeated addition. So it's basically a complex instruction compared to simple addition. And CISC computers or CISC ISAs, you have many instructions of this type. In RISC, which is the reduced instruction set computer, you have simple instructions. For example, you have load, add, save, and so on. Load is simply loading a variable from the memory. Save or store the value in the memory. Add is one of the well-known instructions for adding two numbers and put the result in another variable. Now, the difference between those two is basically if you make the instructions complex, you will have very few instructions, but you will have a complex hardware to deal with these complex instructions. And the RISC, or the reduced instruction set of computers, these instructions are very easy. It's simple to implement. You will have a longer code. The instruction count will be more than the CISC instruction sets, but the hardware is very simple compared to that. Now, the memory types, we have volatiles and non-volatile. The volatile, as an example, you have the random access memory where it will lose its content when the power is off. And the non-volatile, as example, you have the ROM or the read-only memory, and it retain its value. It won't lose it even when the power is off. Now, the microprocessor. Remember, in this course, we are interested in embedded systems that have microcontrollers inside. But we will introduce the microprocessor first so we can compare it to the microcontroller. So basically, it's a single chip that contains the CPU. So you can see here, this is the CPU. We have other things, but the microprocessor is only the CPU. It has the ability to fetch, execute instructions stored in the memory. For example, if you study a computer architecture course, the book by Patterson and Hennessy, they discuss the MIPS instruction set architecture, or MIPS ISA, and they build the hardware around that. The CPU that runs these instructions have 5 stages: fetch, execute, or basically, let me write them down. You have a fetch, decode, execute, accessing the main memory, and then writing back to the register file. These are the 5 stages of MIPS that you might have studied in a computer architecture class. So the CPU is responsible for that. It also has the ability to access external memory. As you can see, that was the 4th stage, and also, or possibly, an external input and output and other peripherals. And we have so many examples. It's very well known, like the Intel Core i3 or 5 or 7 or 9. You have AMD Athlon in desktop and notebooks. We have ARM processor in Apple iPhones. Those are, or these examples are for CPU. That's one, like other example of a CPU where you have a processor for graphics, and here you have 2 cores within the CPU. In the CPU, we also consider the registers and level 1 level 2, and possibly level 3 caches, we consider them as part of the CPU. Now, for the microcontroller, it's essentially a microprocessor plus other modules. These other modules are on-chip memories, I/O devices with different module components, as you can see here. Now, the whole thing here is a microcontroller. Some of these module components is analog to digital converters, as you can see here. Communication modules, like here. You have 2 or 3 examples here, SPI and I2C, and the UART or the USART. It's basically for communication where you send and receive a stream of bits. Or sometimes this is parallel as well. But all of these examples are serial communications. You have timers where you count the ticks. And here we have 4 timers, T0, T1, T2, and T3 in this example. You have many other modules, as you can see. You have the oscillator module that's responsible for generating the clock. You have also an I/O ports, different ports that you can configure as input or output ports, and so on. So basically what we mean by the microcontroller is simply a CPU plus other modules that you can see around it. Or you can see it here. Here, the microcontroller, inside it, you have a CPU, you have a RAM, or you have a ROM, you have input and output boards, you have a clock generation or an oscillator, you have analog to digital converter, digital to analog converter, and many other modules. And based on your needs, sometimes you don't want all of these modules, you want only part of them. Also, as the more feature and capabilities, or as you add more capabilities and modules in the microcontroller, the price will be more. Now, it's good to know that 99 from every 100 processor sales is basically inside a microcontroller. So for the CPUs, if you count how many sales you have, for every 100, you have 99 CPUs are inside a microcontroller, and only one a standalone microprocessor. So the idea of the microcontroller is all-in-one solution. It will have some features. The most important one is the reduction in chip count. In turns, it will reduce the cost, the power, the physical size, and so on. Here are some examples. This is from Motorola, and this is from Microchip Company. You can, maybe if this is the first time you heard about microcontroller, you might not know any one of these, which is expected. But here's the core difference between the microprocessor and the microcontroller. The microprocessor is usually standalone. The microcontroller is a full solution, or an all-in-one solution, as we specified here, that contains the CPU and other modules. From this discussion only, you might think that the price of the microcontroller is higher since you have the CPU and the other modules. However, it's much, much cheaper than the microprocessor. And the reason is the capability or the capabilities and the feature of the CPU is not like a general purpose CPU of the micro or the standalone microprocessors. So it has specified functionality. It doesn't, some of them doesn't even run an operating system. And you have simple modules. These modules can do specific application. And we will see it with more example in the coming few slides. So as we said, the microcontroller or the microcontroller unit is a single chip which has a built-in CPU, RAM, ROM, I/O board, serial board, and these serial boards like the SPI, the I2C, the UART, you have timers, you have many other peripherals, which basically it's a single chip that is full of modules alongside the CPU. While the microprocessor, or we call it MPU, is a pair processor that needs a RAM, ROM, and other I/O interfaces to do any computing job. Now let's talk about the microcontroller main components, and we will define them briefly. So as we said, the CPU is the core processing unit. The RAM is the random access memory for data storage. The ROM is the read-only memory for program storage. The I/O pins or ports could be a different number of pins, commonly 8, 10, 16, 20, 28, 40. We have also 64 and so on. The serial ports, these are the main ones, the I2C, the SPI, and the USART or the UART. And nowadays they are including the USB. The timers, you have a number of timers. In the example that we showed it, we have 4 timers. It could be 1 or 2 or 3 or more timers, depending on the microcontroller itself. It has an interrupt mechanism, which is a full logic circuitry to generate and control interrupt signals. The peripherals are many additional features, as the EEPROM, the pulse switch modulation signals, modules, comparators, and so on. There are many examples of the peripherals. The oscillator generates or controls the input clock, which is the beating heart of the microcontroller, to guarantee a harmonic behavior for the whole machine, which will be a synchronized sequential circuit, if you look at it in general. Now we will see the difference between computers. This could be for microprocessor and also for the microcontroller. We have the Harvard machine and the von Neumann machine. You can see that both of them have an input and output peripherals connected to the CPU. So no difference here, but the main difference is the interaction between the CPU and the memory. In the Harvard machine, we split the memory into 2, data memory for the variables and program memory for the code. While in the von Neumann machine, we have a shared memory space for both data and program. If you can see here, we have many buses that we need to deal with in the Harvard machine. So for the data memory, you have to supply the address and then either read the data to the CPU or store the data from the CPU to the memory. The program memory, usually you supply the address and get the instructions one by one to execute or run the code. In the von Neumann machine, we have only one bus for the address. Here we have 2, one specified for the program and one for the data. Here we have to share both of them in one. That's basically the main difference between them. I tabulated the differences here. In the Harvard machine, it uses 2 separate memory spaces for program and data for program instruction and data variables. While in von Neumann, it uses the same memory space for both of them. In the Harvard machine, it allows for different bus widths. In the von Neumann machine, it limits the operating bus width. The data for the Harvard machine, the data transfer and the instruction fetches can be performed simultaneously because you have a bus for each one of them. because you separate them. In the von Neumann machine, the data transfer and the instruction fetch cannot be performed simultaneously. So you have to do one of them at a certain cycle and the other in another cycle. Here you are creating a control unit for two different buses, so it would be kind of complicated and costly, but here it will be much simpler and cheaper. In the Harvard machine, the processor needs as low as one single clock cycle to execute an instruction. For the von Neumann machine, the processor needs more clock cycles to complete the instruction execution. Since every instruction have variables on them, so you'll have one cycle at least for getting the variables and another cycle for the executing them. The Harvard machine is widely used in microcontrollers and digital signal processing unit, or the DSPs. So basically, everybody is using the Harvard machine nowadays, where you split the data memory from the program memory. And the von Neumann machine is commonly used in our personal desktop computer, or the PCs and laptops as well, but it's kind of an old idea, and usually right now everybody is using the Harvard machine. Now let's move our attention after this discussion to the embedded system and the microcontrollers. So we will start by discussing a very simple microcontroller, see how we basically only touch the surface, and then we will move to defining embedded systems and the application of the embedded systems. So here's one microcontroller. If you scratch the black casing of these microcontrollers, you will find them. It will look like this. This is the external pins, and there is a connection here. Usually it's gold. And you have the chip that have the CPU and the modules right there. This is one example. It's called DS-PIC30. And here you have different micro controllers with different capability. You can see that this one is very small. This one is bigger than this one. You can see it by looking at the pins. We have only 8 pins here, while here we have much more than that. So from left to right, we have PIC12, PIC16, PIC16. We have Motorola. We have, I believe this is a microcontroller from Hitachi. And this is another PIC16 and another Motorola. Now, if I give you one of them and I say, okay, go ahead, take this microcontroller and use it to control a certain system. Right now, you don't have then enough knowledge to connect this microcontroller and program it. So we'll take one of them. And here we took the PIC12 microcontroller. This is like compared to 1 cent. And you can see that it is very, very small. From the looks of it, you see that it has 8 pins. And we will zoom inside to understand the capability of this microcontroller. The name of it is PIC12 F508/509. Usually, the microcontroller names have a number, a family, and more numbers to specify the microcontroller. And also it depends on the company itself. So the microcontroller that we will discuss in detail is one of Microchip controllers or microcontrollers. Microchip is a company. It has or it supplies many type of microcontrollers. One of them is the PIC12. So under PIC12, we have so many microcontrollers. We have different families. One of them is F. So now we have PIC12F. And under this family, we have many members. One of them is the 508 or the 509. As you can see, we have 8 pins. We usually start counting the pins. Looking at the chip, usually there is some distinction here. Either you have something like this, or you have a dot here. So if you locate this extension, you start from the left by counting the pins, and you start counting 1, 2, 3, 4, and then jump to the opposite pin, 5, 6, 7, and then 8. And you can see that each pin of them now has its own description. Usually you have these descriptions in a data sheet that is supplied with the microcontroller. So basically you will go to the Microchip website, you buy this microcontroller, and you can see its data sheet, and it's actually free. You can go to the Microchip website and look for all the data sheet for each one of their microcontrollers. So in this one, we will start one by one to try to understand what are these pins, and what's their job. So first, we have the VDD, VPP, and the VSS. The VDD is the power supply. Usually it's either 5 volt or 3.3 volt. Sometimes it's 2.5 volt. It depends on the microcontroller. We have also the VSS, which is the ground. We have the VPP, and this VPP is the programming voltage input, only when you program the microcontroller. Again, I want to emphasize that whatever application you have, and if you decide to use a microcontroller, you need the microcontroller and how it is connected to the system, which what we call the interfacing. So you need to do the interfacing first, and then you need to do the programming. So to do the interfacing properly, you need to understand what are these pins and what is their functionality. And to do the programming, you have to pick one programming language. So the microcontroller could understand the instruction that you want to give it to it. So any microcontroller should be, or basically any chip, it should be connected to VDD and ground so it can work. And now for this PIC12, VDD is connected to pin number 1, and the VSS should be connected to pin number 8. The VPP, this is the programming voltage input, as we mentioned, and usually it's the same as the VDD. So you have a power supply here, and this power supply, you connect it both here and also here, and you should connect the ground right there. So more pins. We have here the master clear. And now you see that there is a sharing between, or there is sharing of the signals for pin number 4. We mentioned that pin number 4 has VPP, and now also have the master clear. So if that's what we call sharing or multiplexing signals for a single pin. So the master clear is basically resetting the PIC12. And as you can see, it is also active float. So if you give it a 0 signal, it will reset. If it is 1 or connected to VDD, there is no reset. We also have the general purpose input and output pins. And as you can see, we have GB0, GP1, GP2, GP3, GP4, and GP5. Each one of them, if you are talking digitally, they will be representing a single bit, From GP0 to GP5, we will have 6 bits. 6 bits. So you can also notice that those GBs, or the general purpose, they could be input or output. So you can program them as an input. So these GBs will be inputs or outputs, like this. You can also program some of them to be input and some others to be outputs, except GP3 for this specific microcontroller. Now, this exception is based on the architecture of the microcontroller, and they decided that the architects of this microcontroller, they decided that GP3 is only going to be an input. It could not be programmed as an output. The other GPs are bi direction. We have here the oscillator pins. These oscillator pins, OC, or the oscillator 1, oscillator 2, if you decide to have an external clock, you can use these 2 pins. Usually you use this if the clock or the oscillator is a crystal with 2 pins. So this crystal, you connect one of the pins here and the other pin right there. If you generated a clock and you already have a clock signal with a certain frequency, you can insert this clock signal right away in the clock input. And you use those 3 only if you use an external clock source. If you use the internal oscillator, remember, we said that the microcontroller is a CPU with other modules. The microcontrollers, usually they have an oscillator inside them, within them. If you decided to use the oscillator that is inside the microcontroller, you shouldn't, or you could skip these 3 pins. Also, we have this one, which is the timer 0 external clock input, and that's for the timers. Remember, the timers is only for counting ticks, and to know the frequency of these ticks, you should supply it with a clock. So you can use either an internally clock source for the timer or an external one by supply it to pin number 5. More pins. We have the in-circuit healer programming, or the ICSP. We have the data and the clock pins. So we use this for programming the BIC, for programming BIC 12. So now we know the those pins and the functionality of these pins. Now, to be an expert on BIC 12 microcontroller, we need to discuss each module by itself. So we will discuss the oscillator, when to use the external clock, when to use an internal clock, and so on. We also need to discuss the reset, for example, and what are the sources of reset. Is it only the external pin, or there is other event that cause resets? We should also discuss how to connect the general purpose for the GB input and outputs, the GPIO, and so on. And in this class, what we will do, we will choose actually a bigger microcontroller. It's called the BIC24. And this BIC24, we will go through the Venn diagram again for it. And we will also discuss its CPU and all the other modules. If we do all of this, we will finish this class. So first, we will start with the CPU. We will discuss it probably in the next few lectures. And after that, we will discuss each module one by one. So let's continue. At this point, we will show the BIC12 architecture. You can see that this is the architecture, and looking at the architecture quickly, you can see there is a program counter here, and then you have a flash or program memory that has the instruction within them. You get the instruction from there, you save it in an instruction register, and you have the buses that takes part of the instruction based on your needs, based on the ISA of this microcontroller, and you can supply it to the memory where you can access part of it for what we call offset or the immediate values of the instructions. You get it here with another value, probably a base register, to access the file register or the memory, and based on this, you get the data out or store the data in. And you can see here we have the CPU or the ALU, where you have the either an immediate value or the values or the variables that you get from the memory right here. And you have a multiplexer to choose which one you want to use right now. And then you execute using this ALU. And you can see that the result of the ALU, it could be fed back again to the ALU for an incrementing calculation. And basically, this is how the program memory, the ALU, and the file register and the RAM are interacting with each other. Also, we have, this is basically the CPU with the memory. So this is only the CPU. You could say that this is the CPU with the file register, and you can say that this is what we mean by the microprocessor of this microcontroller. And we have other modules like the GPIO, you have the master clear, you have the different timers, you have reset modules, you have timers, you have oscillators like this timers, you have here timer, you have another timer, you have this oscillator, and so on. And reading what's inside these boxes, you can understand what do they mean. We mentioned that quickly. Here, again, we would say that this is the program memory. You have here a data bus for the program memory carrying the instruction word. And now you can see that the instruction width is 12. And this is basically why we call it BIC12, because now the instruction width is 12. And you have sometimes the address extracted, which is the immediate or the offset, and you have a literal data extracted from the instruction word to feed it to the CPU or the ALU. Here is the instruction decode and control unit, which is basically, usually it's part of the CPU. And you also have the program counter, and the program counter will have the address for the instruction, and then you get the instruction and register it here in the instruction register. This is the CPU. This is the data bus, which is the main data bus between the ALU and the memory. This is a very important bus because all the variables, they will move through this bus, the variables that you need for calculating or executing instructions. And you can see that the width of this bus is 8 bits. And because of this restriction, this microcontroller is or the type of this microcontroller is going to be an 8-bit microcontroller. So if you are asked about the type of the PIC12 microcontroller from the architecture, you would say that it is 8 bits because of this important bus width. And so on. Now, looking again to the same architecture, we could say that the highlighted region that you see in red is basically the CPU and the registers and the memory. So if you take out the memory, which is the RAM and the program memory from this red space, you will end up with what we call a microprocessor. Now in the green areas, this is the other modules like the GPIO, the oscillator, reset modules, and timers. This is the GPIO, which is basically the pins that we just discussed. You have the from GP0 to GP5, you have the other pins that we just discussed as well. And again, we said that each pin is multiplexed with other functionality. So this pin could be GP0 or the data for the programming, for programming the ISCP. And to choose between those, there will be hardware within this box or this block that enables you to choose between those two signals. You have also the timers, as we said, here and here. We have reset modules like this one. We have also the oscillator, and we have other modules. As you can see, the choice that we made here, I'm going back now. We choose this simple, small microcontroller among several types. So we picked this one. You can see that this is very, very small compared to other microcontroller or even a microprocessor. And this is why it's cheaper in price. Now let's talk about the embedded system. What do we mean by an embedded system or embedded systems? They are special purpose computer system, usually completely hidden inside the device that it controls. So usually they are a board, and within this board you have a microcontroller, and it is hidden inside the system. You cannot see it from the outside. It has a specific requirement and performs a predefined tasks. So now we know any embedded systems, whatever the application that you have, it should have a microcontroller within the embedded system that's usually part of the bigger board or PC. The cost reduction, it has, one of the advantage of the embedded system is the cost reduction. And if you compare this to general purpose computer, the CPU is maybe hundreds or sometimes thousands of times more expensive than a microcontroller. They differ in many criteria, like the performance, the reliability, the cost, the power consumption, the size, the testability, or the design for testability, and also the safety. The more properties or features that you have in the embedded system or in the microcontroller, the pricey it gets. So let's have some application or some examples so you have a better picture of what we mean. This is an example, which is a clock. We use a microcontroller, and this microcontroller, we could connect to it an LCD, which is basically a screen in port A, and we could connect 3 switches. This is the switches, usually the circle plastic that you see here, you can remove it and you bring, it will be like this one. So we choose these three switches for port B, C, and D. And you need a power supply that's connected to a power supply unit. And you have now interfaced the system to have a digital clock. So your system, it is a digital clock. From the outside, it should be wrapped within maybe a plastic box. And inside it, you have the microcontroller with its board connected to switches, the LCD, and also the power supply. Now, as you can see, we only use the GPIOs and the power supply. And we will definitely use the CPUs, maybe the interrupt modules, and maybe one of the timers. The rest of the modules, we don't really need them. And this is now the advantage of microcontroller. You could choose a cheaper microcontroller that satisfies your system needs. This is the interfacing of this system. And now for it to work, you need to program the microcontroller. You need to push code in the program memory that the CPU can run and give you what you expect in the LCD. And also it interacts with whatever you choose on these switches. These switches, right now, you don't know what exactly their functionality, but since this is a digital clock, you should make one of them for changing hours and another for changing the minutes, for example, and the last one maybe for an alarm functionality and so on. That's one example. Another example is the embedded system within the refrigerator. Any refrigerator, like current ones, not the really old ones, they are kind of what we call a smart refrigerator because they include a microcontroller within its embedded system. So you can see that here you have a human interaction with the refrigerator, and it should have a microcontroller, or what we call here the embedded computer within a board. It reads the actual temperature and the required temperature, and based on the inputs that it has, it displays some results if the refrigerator had an LCD screen, or it controls the compressor. If the temperature is high, it will run the compressor. If it is very low, it will stop the compressor. Also, it could have an alarm system. For example, if you have children and they open the door and they kept it open, the alarm system will sound after waiting for a certain number of seconds. And that's why we need a timer inside the microcontroller to count how many seconds has passed since you open the door. Possibly you have a network interaction where the refrigerator can, or your fridge could connect to the outside world. It has an IP, and based on the fridge needs, it could interact with the shop, for example, and tells it that it needs certain vegetables or certain meats. And so you can see that we have now two different systems, and both of them have embedded systems inside them. And inside each one of the embedded system, we have a microcontrollers. The applications are huge. There are so many different applications. These are some typical applications. The cell phones have microcontrollers inside them. The car accessories, it has a board usually. Right now, all new cars are smart or have some smart capabilities, so they need to have an embedded system within the car. The digital locks, the drones, temperature controls for controlling either AC, a fridge, maybe a pool, any kind of space. And you could write many different applications for the microcontrollers. You can pause the video and see if you know more than this. Actually, in your room, only the room that you are sitting right now, or even if you are outside, you can see many embedded systems around you. I'll give you even more examples. So if you want, pause now and see if you can have more than that. If you continue, this is more applications like the smartwatch, the pager, even though it's kind of old, the calculators, all the peripherals of the computer, like the keyboard, the mouse, and so on, the modem, the power bank, the fridge, as we said, the AC, even the remote control, the toys like video games, the controllers themselves, or the maybe the DVD or the Blu-ray reader. Also, you have the toy cars, basically all the video or all the games in general. If they have a battery, usually they have embedded systems within them with certain capabilities. And you have many home appliances like the alarm clock, the thermostat, the air conditioning, the hair dryer, the washer, the microwave oven, so many. Now, how to buy, let's say that you want to build one of them, or you have a new idea, and this system needs to be smart, and you need a microcontroller that you need to interface and program. Where do you get this microcontroller? How to get them? There are so many companies that can give you microcontrollers. Manufacturers offer a range of devices from low end, and usually they are very cheap, to high end application. You can see these are by or these are some of them, not all of them. You have Apple, Philips, Freescale, Siemens, Intel, Haltech, ARM, Epson, NXP, and you have so many. Now, in our class, we will choose one of microchip microcontrollers. And we mentioned this several times. The microcontroller that we are going to choose is BIC 20, and with a certain family, with a certain number. And we will mention it later in another lecture when we try to look at the pins and what are the functionality of these pins, and whenever we discuss any of its modules. Also, it's good to mention that usually for educational purposes or sometimes graduation project, they use Arduino microcontroller or Raspberry Pi. Now, how to choose the best manufacturer? What's the best device? This is an open-ended question. It's basically based on your needs. Some of these microcontroller, they are less than $1 in cost. And some of them have few hundreds, some of them even 400 or 500. It's basically based on the capability that you want. Here are some of the things that you need to be knowledgeable about, like the microcontroller performance. You have a processing power. Some of them have, we will give some indication of the processing power by knowing how many bits that you are dealing with. So you have 4 bits. This is in the data bus. Remember the BIC 12? We said that the bus have 8 bits. So the BIC 12 is of this processing power. So you have 4-bit microcontrollers, you have 8-bit microcontrollers, you have 16-bit microcontroller, and 32-bit microcontroller. For the microcontroller that we are going to study, BIC24 is actually, or its type is 16-bit microcontroller. Now, that's one website, the microcontroller.com. They say that, or they claim that the highest rate of new product success is in the 8-bit market, which is in this market here. The lowest rate of success in the 64 or the 32-bit microcontroller market, which is this one. Now, you know that your PC or your laptop, usually it's 32-bit or 64-bit. But for the microcontroller, the current microcontroller that have or that are really implemented within systems around the world are the 8-bit and the 16-bit microcontroller. So there's specific features, and we said that when we talked about the modules, some of them for communication, for the keyboard handling, the signal processing, the video processing, and so on. Sometimes you need Bluetooth there, you need wireless connection. Sometimes you need the microcontroller to have support for a lightweight version of the operating system. Sometimes you need a microcontroller within a board that have a USB connection. It depends on the application that you want. Now let's review some fundamentals that we need to understand really well at the beginning of this class. So when we say a program, it's a set of statements for a computer written in a programming language, which implements an algorithm, usually passively residing in the drive. So you need a programming language to write a program. This programming language in our class, we will use the C programming language. Many university, usually they teach students and the first year Java programming language. The C programming language is very close to the Java programming language, and we will give a lecture about C programming, but we will introduce the C language for our own needs. So we will write down the C language in such a way that makes it closer to micro controller and programming the microcontroller. Now, the assembly code is a set of instructions converted from the high-level program by an assembler. So the program, if you write in C, you use a compiler, and now the compiler will generate the assembly code for you. And the assembly code is basically the instructions. And in the beginning of this lecture, we said the difference between the CISC and the RISC. This is usually in the assembly level. In the machine code, it's the assembly instructions that are coded and flashed to the program memory in the forms of zeros and ones. Now, the process is an active program that resides in the memory currently. So if it is in the hard drive, it is in the drive, it's a program. If it is in the memory, meaning that it is not passive any longer, it's actually active. And this is what we call a process. Now, a page is a logical block of memory or a drive that refers to a specific memory consecutive locations. So it's basically a chunk of data that is in the drive or the memory. A bank is a logical unit of memory determined by the number of bits in a column and a row per chip, multiplied by the number of chips in a bank. So this is what we mean by the bank, and usually it's each memory have a set or a specific number of banks. The pointer is a register or a memory location that contains the address of an object. So the pointer points to the location of the data. The stack is a last in, first out, or LIFO data structure, which contains information that are saved or pushed in the stack or restored or popped in from the stack pointer is a register that contains the address of the top of the stack. So the stack pointer points at the top of the stack where you can push and pop data from the top of the stack. The program counter, or PC, is a register which holds the address of the next instruction to be executed, which is incremented after each instruction fetch. So you know the 5 stages, for example, for MIPS CPU, you have fetch, decode, execute, reading the memory and writing back to the register. So, and the fetch, on the fetch stage, which is the first one, you need the program counter to tells you which instruction to fetch. So it contains the address of the next instruction. We have also interrupts, which is an event that suspends the main program execution. It interrupts it while the event is served or handled by a program. This program is called the ISR, or the interrupt service routine. So the CPU would love to continue execution without any interruption. But sometimes you need these interrupts, usually from an I/O or from other modules, that it tells you that a certain event happens. Since there are different types of interrupts, you need an interrupt vector, which is a memory location which holds the address of the first instruction of each of the interrupt service routine. So if you have, let's say, 20 different interrupt service routines, so you need to have 20 different addresses for the beginning of each one of these 20 interrupt service routine, and you store them in the interrupt vector. Usually it's in the memory. The machine clock, which is the beating heart of the microcontroller or a microprocessor in general, is fixed frequency signal that triggers or synchronizes the CPU operation and events. Now we will see these 3 definitions. You need to be careful about these 4 actually definitions. The machine clock frequency, which is denoted by FOC, or the frequency of the oscillation. This is the rate of the clock oscillation in a single second, which is usually measured in megahertz, sometimes in gigahertz, and it's referred to as the oscillation frequency. Now, related to the FOC, we have the TOC, which is the machine cycle, which is basically the elapsed time for the system clock to repeat itself. So let's look at this here. So if you say that you have the frequency of oscillation is equal to 80 megahertz, if you take the reciprocal of this value, which is 1 over 80 megahertz, you'll end up with 12.5 nanosecond, which is the machine cycle, or the TOC. Let's look at it here. You can see that the machine clock in this example, to be able to draw it clearly, in this example, you have the machine clock. The FOC is equal only to 4, meaning that the TOC is going to be 1 over 4, which is the 0.25. So 0.25 you have for each clock, you have 0.25 seconds. So if you say that within a second, within a full second from here, 1, 2, 3, and 4 to here, you have 4 clocks, or you repeated this clock 4 times within 1 second. And this is why the frequency is equal to 4. Each one of these clocks is 0.25 seconds. Now, let's continue. The instruction cycle. Here we call them machine clock frequency, machine cycle. Now, when we say instruction cycle, this is the elapsed time for a microcontroller to complete the execution of a single instruction. So here we are interested on the instruction execution. This is basically including the fetch, decode, execute, and write back the results. Now again, if this is the instruction cycle, then the reciprocal for that is the instruction frequency, which is the rate of the instruction execution in a single second. And usually it's also measured in megahertz, like the machine clock. In our microcontroller, which is PIC24, FCY is equal to FOSC divided by 2. Why? Because we have, or we need, 2 machine cycles to execute a single instructions. So for only a single instruction cycle, we need 2 machine cycles for the instruction to finish execution. And because of this, we say that we need FCY equals to FOSC divided by 2. Again, let's see this example here. Now, since we said that the FOSC is 80 megahertz, and by the way, this is the maximum frequency of the PIC24. So if you have the maximum frequency, now the frequency of the instructions, or the instruction frequency, FCY, is equal to FOSC divided by 2, which is going to be 40 megahertz, or we can say that it's 40 million instruction per second. Now, looking back here for this simple examples, now, if we say that this is the machine clock where FOSC is equal to 4, the instruction clock, if you calculate or if you adopted our microcontroller, which is the PIC24, FCY would be 4 divided by 2, which is equal to 2. So FCY is equal to 2, meaning if you take the reciprocal of this, you have 0.5 seconds for each instruction cycle. This is one full instruction cycle, and you see that you need 2 clock cycles for the instruction, for every instruction cycle. You have this the first, and this is the second cycle. And now you can see for a full second, you have 2 instructions cycles, meaning that the frequency, or the FCY, is equal to 2. This marks the end of this first lecture, and the next few lectures, again, as I mentioned before, we will talk about the CPU of the microcontrollers and the different modules. But before digging deep, we need to give you few lectures. Like one of them, we will discuss the C language, and then we will discuss the CPU of the PIC24, and then we will jump to every module of the PIC24 to understand how to deal with this type of microcontroller. And then once you are familiar with microcontroller, this will mark the end of this series of lectures. So I'll see you next.